So the next thing I wanted to do is actually calculate the area of an ideal triangle. And this is something that I haven't done in previous classes, but we have a lot of time on our hands, so I thought, why not? Usually I just state it as a fact, but it's not too hard if you know a little bit of multivariate calculus, and so we might as well do it just so I can kind of prove to you that it's not so scary. So, all right, so I've got some hyperbolic space. I'm just drawing a piece of it. So this is the hyperbolic plane. And remember, there's many of them depending on sort of how curved they are. So let's say this is the one of radius rho. And what does that mean? It means that under my map to the upper half plane, the distortion between the Euclidean distance here and the actual distance in hyperbolic space is given by rho over y, right? So that's how you can calculate the radius, by figuring out what this distortion factor is. But let's just assume it's given to us, and it's some number rho. And I want to calculate the area of an ideal triangle. So there's many ideal triangles, of course, on this upper half plane. And when I map them to H, some of them look like this, and then others maybe have vertical lines as two of their geodesics, just depending on where certain geodesics here get mapped to under this map M. Okay, but this picture is a little bit misleading because actually, like I said before, there's an isometry between these two ideal triangles, and you can prove that if you want. It takes a few steps of work. It's not automatic, but with a little bit of work, you can prove that from our hyperbolic worksheet 2, which talked about the isometries of the hyperbolic plane and what they corresponded to in terms of maps of the upper half plane. We used those matrices, those 2x2 matrices, right? And you can show that there exists one that takes this blue ideal triangle to this red ideal triangle. And what we deduce from that is that all ideal triangles, since they're all congruent, they are all the same size. And what I want to do is calculate that size. Okay. And so let's see if we can do that. So they're all the same, so I can use the simplest ideal triangle I can draw to do my calculation. And so the simplest one I can think of has as its geodesics a semicircle of radius 1 centered at the origin, and then the other two sides are given by the vertical lines at plus and minus 1. Okay, and so what I want to do is I want to calculate this area, but taking into account the distortion factor. Okay, and so the idea from calculus is I work kind of infinitesimally, and so let's say I want to calculate the area of this whole space. I do it by calculating the area of rectangles, which are contained in the space, and then I add up the area of all those rectangles, and that should be my final answer. So what I need to do is figure out the area of some little rectangle. Let's say it has width given by delta x and height given by delta y. I want to figure out the area of this in the hyperbolic sense. So this corresponds to some region on the hyperbolic plane, and I want to calculate that area. And then I'm going to add those all up. I guess this region is in an ideal triangle, so actually it would be in here maybe, right? Okay, well, the hyperbolic distance of this segment is given by, so the hyperbolic width of this rectangle this little segment here is, well, it's delta x times this distortion factor of rho over y, where y is the height that segment's at. Okay, we already said that. The vertical one's a little more tricky because, of course, the height is changing, right? So the distance of this blue line in the hyperbolic sense is, I mean, it's not quite delta y times rho over y, because you know, the height here is larger than the height at the bottom. However, it doesn't change that much, assuming delta y is really small. So this is approximately true. If we assume that delta y is really small compared to the height y. Okay, so it's not an exact value, but it's a good enough approximation. And as you know, with integrals, eventually we shrink our delta y. We take a limit as delta y goes to 0, and so this assumption that it's small compared to y is reasonable because we're making them basically arbitrarily small, these delta y's. And so finally, the area, the hyperbolic area, of this rectangle in hyperbolic space is the product of these, so it's going to be delta x times rho over y times delta y times rho over y. And of course, this is an approximation. So I can simplify this to rho squared over y squared, delta x, delta y. Okay? And so the area of the ideal triangle, hyperbolic, in the hyperbolic sense, well, I'll say the area of the ideal triangle in hyperbolic space is going to be the sum of all the rectangles approximately. In this region, the sum of the hyperbolic area so I'll say it this way, the sum of rho squared over y squared, delta x, delta y, for all the rectangles inside of here. So if I calculate this number for each rectangle and add them all up, that gives me an approximation of the hyperbolic area. How do I get the exact value? Well, I do the integral, right? So I replace the summation with the integral, and so I'm integrating over this region, right? And what I'm integrating, the integrand is the thing that I'm adding, so these values, and so this is rho squared over y squared, and these become infinitesimal, so dx dy. Okay, and so what I need to do next is figure out what the bounds of integration are, and then I'll be able to do the integral. And these bounds are just determined, you know, I need to choose bounds that cover the region here of the ideal triangle. So let's draw the picture again carefully down here. It looks like this. Okay. So I set this up so that I'm doing the y bounds first, which is a good idea. It's going to be easier that way. And the y values go from, oh, this is a bad idea, actually. I should do x first, because the x bounds are easier. So the x values go from -1 to 1. Right? And then for all the x values between -1 and 1, which y values do I care about? Well, I care about the y values. I'm looking at the y's which are above this semicircle. Now this circle is defined by the equation x squared plus y squared equals 1. And so what y values am I looking at? Well, the circle is defined by, at least the upper part, is given by positive square root of 1 minus x squared, right? And so I'm looking at all y values above that to get this ideal triangle. And so my y bounds go as a lower bound. I'm going from 1 minus x squared, square root of that, and as an upper bound, I'm going to infinity. And so this is the exact value, whatever it is, this is the area of an ideal triangle. And it depends on which hyperbolic space I'm in. It depends on this radius rho. Okay, so now all we need to do is calculate this integral. Let me rewrite it. Yeah. Rho squared over y squared dy dx. There we go. Okay. How can we calculate it? Well, the rho is a constant. It's just the radius of the hyperbolic space, so I can pull that out. And so now I integrate first with respect to y. So the antiderivative of 1 over y squared is negative 1 over y, right? So this is equal to rho squared. So far the x part's just going along for the ride. Negative 1 over y. This is a little bit abusive notation, as many of you know. From 1 minus x squared to infinity. That's the abusive notation. Technically, we should write this as a limit. Dx. Okay, so like I said, technically this is an improper integral, this integration with respect to y, because I'm going to infinity, and so I should be taking the limit of this value as y goes to infinity. That's just 0, and so this infinite part doesn't contribute. And what I'm left with is this evaluation here. So I get rho squared, negative 1 to 1. The infinite part gives me 0 minus negative 1 over, and then I evaluate here, so 1 minus x squared square root dx. Okay, so I'll write this a little more cleanly. It's just 1 over square root 1 minus x squared dx. Okay, so at this point you're looking at this and you're probably having some flashbacks, some PTSD. You know that this is a scary looking integral, and maybe you have a suspicion that if you go and look up like antiderivative tables, there's one in there that tells you what the antiderivative of this is. Or maybe you remember what the antiderivative is. For me, I didn't remember, and I didn't feel like looking it up. because we can actually solve this if we're a little clever using trig substitution. Substitution, which I know is probably not your favorite thing, but it's not so bad in this case. So what do I mean? Even if you haven't seen trig substitution before, it's just a fancy form of u substitution using trigonometric equations. So I look at this. This takes a little bit of experience, but I look at this 1 minus x squared, and what I think of is sine and cosine. And the reason is sine and cosine have this beautiful property that cosine squared plus sine squared of any value is always equal to 1. And so when I look at this, I say, oh, well, if I plugged in cosine or sine in for x, then I could simplify this. So in particular, let's see. So let's let x equal sine of u. And this equation is telling me that cosine squared u is equal to 1 minus sine squared u. If I let x equal sine of u, then this 1 minus x squared is 1 minus sine squared u, and I can plug in a cosine squared, which is great because then it'll play nicely with the square root. Okay, so I'm going to do this u substitution. If x is sine of u, then dx is cosine of u du. So I have to make that substitution in as well. And so this integral is equal to rho squared, and now I'm going to integrate with respect to u instead of x. So if x is sine u, this 1 minus x squared, this is equal to 1 minus sine squared u, so I can plug that in there. So this becomes 1 over the square root of 1 minus sine squared u. And then dx is cosine of u. So far it doesn't look simpler, but remember that this 1 minus sine squared u is just cosine squared u, and so this becomes rho squared integral 1 over square root cosine squared u, cosine of u du. And this square root was always positive, right? Because we were looking at the upper part of the circle. And so square root of cosine squared u is just cosine of u. So that cancels with that, and I'm just looking at the integral of 1 with respect to u. Okay. Now, the one thing I've neglected, as I'm sure some of you have noticed, is I haven't written out what these bounds are in terms of u. Right, so we need to figure that out. So to figure out the bounds, we remember what our x bounds were. X went from -1 to +1. And so if x is -1, what is u? Well, the sine function looks like this. And x is -1, so x equals sine of u. So this is my u axis, this is my x axis. I achieve a value of -1 when u is equal to negative pi over 2. And I achieve a value of +1 when u is equal to pi over 2. And so those are the bounds that I need here. So this goes from negative pi over 2 to pi over 2. And now I can finish the integral. So this is just equal to rho squared. Antiderivative of 1 is just u, so u from negative pi over 2 to pi over 2. And I get 2 times pi over 2 times rho squared, so I get rho squared pi. So that is the area of an ideal triangle in a hyperbolic space of radius rho.